today we're going to, because we've already missed two, yesterday took me an hour and 20 minutes to get out of, not yesterday, Friday, took an hour and 20 minutes to get out of my driveway using roofing shingles left over from constructing my house, so put them in front of my wheels. At some point it'll be paved, but for now it's just messy gravel, so hopefully we won't have any more bad snow. All right, but anyway, we missed 2 lecture days due to snow, and so we do need to keep moving along here. And today we're going to start with some things that will not be on the test, but I'm going to assign some homework that will be due not the Monday after the test. I'll give you a little bit of a breather, but the Wednesday after the test on completeness. So again, let's let F be an ordered field. Now, I've said before that there are lots of ordered fields, right? You're very familiar with the rational numbers, and in fact, when you're actually doing things in the real world, instead of symbolically, like using a computer, then that's all you got available to you, right? The rational numbers. But as it turns out, it's extremely useful to actually have the real numbers at your disposal, right? Even though you can never actually write down the decimal expansion or something for a real number because it's infinitely long. Nonetheless, numbers like the square root of 2, which you've been told anyway, is irrational, and we'll actually prove that in here, okay? So, and pi and e, these are all things that you've been told are irrational numbers, and they're extremely useful, okay? You could actually get by sort of with just the rational numbers, but it would be a complete nightmare, okay? And somehow, using the real numbers allows you to facilitate what you're doing, all right? I mean, surely, the square root of 2 exists, right? Because, you have a square, and that's what the diagonal is, and you can prove that. And in fact, this was a real irritant to people for a long time, that the square root of 2 was not a rational number, right? In fact, the legend is the guy who originally proved this, one of the Pythagoreans, I guess it was a guy, I don't know, maybe it's not clear what the gender of this person was, but back then, most of the people who did scholarly things or were allowed to get education were male, but at any rate, the person who did this was actually drowned for his insolence, because the mathematics and religion were kind of related, and that actually they didn't get separated till like the 19th century, which is about the same time that people began to really, so it was a couple thousand years before people actually understood how to deal with irrational numbers. Took a long time for people even to get used to 0, okay, so, let alone, and negative numbers and so on, right? But we don't have any of those issues now, right? I mean, you all understand negative numbers, right? You presumably balance your checkbook and know what happens when it becomes a negative number, right? It's not a good thing, okay? But it is a real thing that you can deal with. Okay, and likewise, real numbers are well, they're real. And they're things that are extremely useful. In calculus, you learned about sequences. I guess if you've had, some of you may not have had Calc 2, I think is where you usually do sequences, right? And, convergence questions, right? And you have all these lovely tests for, when, for example, an increasing sequence converges to something, right? Well, but actually, if there's things missing from your ordered field, like the square root of 2, you might have something that converges according to those tests, but actually doesn't because there's nothing there for it to converge to. So the thing that fills in all the holes, it does 2 nice things for us. First of all, it fills in all the holes in an ordered field, right? So that if something ought to be converging by these tests that, that should make sense to you, right? Then it actually does converge to something. There's not a hole there, right? So it fills in all the holes. The second thing it does, and I've mentioned this before, is that it makes the real numbers unique. Okay, so this is the completeness axiom, and there are lots and lots and lots of ordered fields. Some of them are really weird. You wouldn't want to try to do regular calculus with them, but they're useful in other areas. They're called non-Archimedean ordered fields. Okay, and if any of you go into certain areas of mathematics in the future, you may have cause to work with those. But you don't want to do ordinary calculus with them. Okay, they have kind of weird properties. But once you add in this last axiom, that's the only one. The real numbers are it. Right? This can be proved. We obviously can't do it in here because it's hard, okay? But it can be proved that it's the only ordered field. So then you can safely use it to build your bridges and whatever and not worry that, ooh, maybe there was another way to do this with a non-Archimedean ordered field or something. And well, no, actually, okay. Okay, that's it, right? Okay. So we're going to add one more axiom, but there has to be a little background. This is kind of a complicated statement that's not quite as simple as just, the associative law or the existence of zero or the ordering and all that. It's not something you will have seen before, although you have, I assume, seen things like, upper bounds and lower bounds and least upper bounds and that kind of thing. Okay, so we'll start with the definition. So again, F is any ordered field so far. Let A subset of F be non-empty. You can define these things for the empty set too, but it's just irritating and we won't do it. Then some M, an element of F, is called an upper bound of A if, okay, so you know what an upper bound is, right? I mean, you've dealt with these. It's something that's bigger than everything in the set. Well, we got to be a little more precise in that, right? So if for every x an element of A, x is less than or equal to M. Now, one of the dangers of what we're doing in this section is that sometimes it's easy to draw a simple picture and decide, oh yeah, that's true, it's obvious or something, right? But remember what obvious means in here. It means that you can immediately write down a one-line proof of it, okay? And so many of the things that seem obvious aren't obvious according to how it's defined in this class. And so, you've got to get used to writing down careful proofs of these things and not just drawing pictures. Okay, but having said all that, pictures are useful to help you think about things. It's just that you have to then go from the picture, just like you did with set theory, go from the picture to actually writing down a proof using, and these things all have their standard opening lines and so on, right? But the idea is that if this is your set A, and you also have to stop thinking about sets as being intervals, okay? I mean, there are some really, really, really complicated sets in there, right? That things you've never dreamed of happen, okay? Fractal kinds of things, okay? So, right? So, so don't think of sets as, there could be big holes, little holes, infinitely many holes, okay? There are all kinds of things that could be there. So you shouldn't think of sets, so I'll usually draw them like this, right? But the picture is that, well, there's your M. And in the picture, of course, it just means it's to the right of everything, okay? But what it means according to definition is that if I pick up any x in here, x is less than or equal to M. And the usual left and right business still works here, right? The picture is still the way you would have thought of it before, but you're going to have to prove stuff by writing things down. Okay, so having said all that, this is a for all statement. For every, for all, right? What would be my opening line to show that M is an upper bound of A? I'm not actually proving anything now, but there's a standard opening line, and what is going to be? Yeah, right? A for all statement, usually what you do, I mean, it's not always true, but in here, usually it's true. The best way to start is to pick up something that's supposed to satisfy this property and then work with it, okay? We're not trying to prove anything now because I don't have any hypothesis here, right? But the point is, your opening line should always be, let x be an element of A. And you're trying to show what about x?
That is
it's less than or equal to M. That's it. Okay, now of course the proof might be harder than that, okay, but that's your beginning and your end, right? Let x be an element of A, and then you want to end, excuse me, with x less than or equal to M. That's it, okay? It's of course the details that are, sometimes a problem, right? But nonetheless, that's the whole picture there, okay? So if S is an upper bound of A, and for every upper bound of A, let's give it a name, sorry, M of A, S is less than or equal to M, then, okay, so you learned at some point, probably you've heard the words, you learned what something like this is called, right? If you have an upper bound that's less than or equal to every other upper bound, what did you call that? Well, if it's less than or equal to every upper bound, how is it, It's the least upper bound, okay? But of course, we're not going to use that terminology for a couple of reasons. First of all, it can get confusing when you're doing serious proofs, and also we're going to use the, the sort of more advanced term for this, which is the supremum. Then S is called a supremum of A. Okay? You've known it as least upper bound, but again, from years of doing this, I know that that gets confusing, and this is the term that you'll see in other math courses as well later on. And last, if S is a supremum, right, of A, and S is in A, then S is called a maximum of A. Okay, and so you're already maybe thinking, well, a maximum, there's only one maximum. Okay, well, we're gonna prove that, okay? In fact, there's only one supremum. That's something we'll prove in just a minute. But before we do that, I want to mention, and some of your exercises will involve just translating here, right? But we can use the same definition to define lower bound, okay? So what am I going to change in this sentence here?
X is greater than or equal to
Yep.
L?
Well, we can continue calling it, okay, M, just to be simple. Okay, well, if you want to call it L, then we got to put an L there, okay? That's fine, we can do that. Okay, and then so this one, right, there's something called an infimum instead of the supremum, okay? So let's call this one I. So how do I change this now? Lower bound of A, and for every lower bound, M, we want to call this L if you want, of A. And how do I change this?
I is
Greater than or equal to L, then I is called an infimum of A. Okay, so you're going to work with this one. All the statements that we prove about the supremum have analogs for statements about the infimum. And generally, you're just replacing lower bound by upper bound and reversing some inequalities, okay? So you'll have to, and some of the statements, I'll just say, okay, there's an analogous statement, right? And other statements that we will actually prove them, or I'll ask you to prove them, okay? But these are two things. If you understand the supremum, then really understanding the infimum is really not any different, okay? It's really not any different. Okay. Any questions about these definitions now? You'll get used to them after a while. Again, the usual way to learn these things is to actually work through a few problems on them. So let's start with the following lemma. If A subset of F is non-empty and has a supremum, then the supremum is unique. So we have two things we have to be thinking about here, right? We define this new thing called supremum. And the question is, does it exist? And is it unique? Okay, and in general, I mean, these questions can have no as an answer. All right, and so actually the first and easiest thing to deal with is the uniqueness of it. So let's go ahead and prove this. Okay, so what's the usual way to prove uniqueness for something? Pick up two of them, and then what? Show they're the same, okay? This is even how you can prove that the real numbers are unique, right? Pick up the real numbers here, pick up some other complete ordered field here, and show they're the same. It's just a little more complicated, right? Because then you got to show that there's a function between them that preserves all the operations and everything, right? So it's quite difficult. But the idea is the same. Pick up, suppose there are two of them, show they're the same. Right? This is one of the standard ways to prove uniqueness of things. So let's suppose S and S prime are suprema of A. So let's suppose we have two of them. Okay, so we have basically two properties, and I'm going to separate these out and give them names in a minute, right? But what are the two things that a supremum is?
Upper bound.
It's an upper bound, and for every other upper bound, it's less than or equal to it, okay? So, since